Salam sejahtera and good afternoon to Dr. Nas. Today, we would like to present our video assignment with title Journey to Mars, exploring the physics of traveling Mars by using Hohmann transfer and its alternative methods. This presentation made by Zhen Hong, Vincent, Zongyun, and Johan. This presentation consists of 5 parts. The first one is background of Mars travel, the second is theory and its equation, the third one is Hohmann transfer, and then followed by alternative way to transfer orbit, and then the final one is the derivation.
This slide is about background of Mars travel. Mars travel represents one of humanity's most ambitious endeavors, bridging the gap between Earth and the red planet. To enable such missions, a clear understanding of Mars and the dynamics of interplanetary travel is essential. Now let's take a look at the basic information of Mars.
These are theory and equations we have used in the assignment, such as conservation of energy and escape velocity, Weiss-Weber equation for velocity, and also the period of solar central orbit, followed by the sphere of influence semi-major axis for transfer orbit, and the time taken to transfer the spacecraft in the HRT. These are some advantages of Hoffman transfer. First one, the energy consumption is minimum. Second, it is easy to manipulate. Third, it is widely applicable, and last but not least, its predictable trajectory, making it reliable for interplanetary missions. The Hoffman transfer is a highly efficient method for moving a spacecraft between two orbits around a central body, such as the Sun. This technique involves two engine burns. The first burn places the spacecraft into an elliptical transfer orbit, and the second burn adjusts its velocity to match the target orbit.
The entire process of Hohmann transfer involved 4 stages. First, the spacecraft will leave from the Earth. Then, it will travel in the transfer orbit. After that, it lands on Mars. Eventually, the whole process repeats again for a back trip to Earth. For each calculation, we assume that the orbit of the Earth and Mars around the Sun nearly to be circular. Now we will look into the details of the Hohmann transfer process. The first stage is leaving the Earth. To leave the Earth, the spacecraft must achieve the minimum escape velocity about 11.2 km per second relative to Earth. Then is a stage 2, which the spacecraft have to travel in the transfer orbit with the required velocity of 32.75 km per second. Note that the sphere of influence of Earth is 6.18 times 10 power of 8 meter. When the spacecraft arrives at the Mars orbit, its velocity must boost up to 24.19 km per second to travel in the Mars orbit. Then, the spacecraft is catch up by Mars within the sphere of influence of 9.06 times 10 power of 8 meter.
In stage 4, when Mars and Earth are in a suitable position, the spacecraft is ready for its return journey. It must achieve the escape velocity of Mars, which is 5.01 km per second, in order for it to overcome the gravitational force of Mars and escape to the outer space. After escaping from the gravitational influence of Mars, the spacecraft will enter the circular orbit of Mars. The required velocity equals the orbital velocity of Mars, that is 24.1 km per second. Then, the velocity of spacecraft is reduced in order for it to enter the elliptical orbit at the aphelion. Through the elliptical orbit, the spacecraft will arrive at the perihelion with velocity of 32.7 km per second, which is greater than that at aphelion. Finally, the spacecraft will enter back to the Earth with velocity slightly higher than Earth's escape velocity. Three components are taken into consideration when we discuss the time required for Hohmann transfer, which are the time needed to and back, and also the time on Mars. From equation 9, the time for forward and return journey are the same, that is 258 days. For reposition purpose, it takes 460 days. Hence, a total of 976 days are needed for the whole journey, which is around 2.67 years. There is also an alternative way for the transfer of orbit. For the modified HOT trajectory, by using an additional field, time taken on Mars could be reduced. However, spacecraft would encounter high solar radiation, which turns into a challenge for the trip. The whole journey would only take 18 months.
Now let us to go through our final part of our presentation, which is the derivation of equations. We derive the Weiss-Weber equation by using law of conservation of energy and conservation of angular momentum. Then, we take the positive square root of right-hand side to obtain the magnitude of velocity. Then, by assuming the orbit almost circular, we obtain the most simplest form of Weiss-Weber equation. Besides that, we also derive the escape velocity on Earth and Mars. Furthermore, we also derive the period of the orbitary motions, which we reduce into most simplest form by comparing with the Earth. At the end of the video, here is our references of our assignment. Thank you for watching this video and wish you have a nice day. Bye bye.